All right, on Friday, I introduced momentum, and today I'm going to focus on problem solving in momentum. Now I have the list of things we're going to be doing: inelastic, elastic collisions, two-dimensional collisions. We're not going to actually do two-dimensional collisions. I will mention just briefly what the difference is, but it just requires you to use trigonometry and the same principles as one-dimensional collisions, so I'm going to be happy to do one-dimensional collisions. But first I have some cool demos which are going to kind of link between energy and momentum. And we start with this one here. This is a bunch of super balls. 3 super balls on this thing, and I put a 4th one on top. Here. Super ball, bounces. Not so super.
Super Bowl?
Well, this one singular would be like. One thing we talk about with these is the coefficient of restitution. If it falls and bounces and comes back up to my hand, which that clearly didn't, then we say it had a coefficient of restitution of 1, meaning that after it bounced, it had 100% of its initial kinetic energy that was returned after the bounce. So how can I determine, based on dropping this, how much energy as a percentage is returned? How high it bounced? Because it starts with what kind of energy does it start in my hand? Potential. Potential, because it's based on position. Then when I drop it, it's going to convert that into kinetic. When it hits the ground, some of it will be absorbed by the ground, going into things like, well, heating or making some noise. Those are forms of energy, because energy cannot be created or destroyed. We'll learn that in a month or so. And then it comes back up, and that kinetic energy that was returned to it on the bounce, then it's converted back to potential. So I can just take the height it started, mgh initial, the height it ended, mgh final. If I take the ratio of those two, I just have the final height over the initial height is equal to the energy final over the energy initial, and that tells me the coefficient of restitution. So this here has a coefficient of restitution. It's just a little better than 0.5, right? It's not great. All right, so, and these would all be similar.
Can I have that ball?
Excuse me?
Can you see that? Yeah.
I have 2 more, so I'm good with letting her see it. So now I'm going to take this, and I'm going to try to drop it vertically. If I fail, well, I fail. What's going to happen? Has anybody seen this before?
No.
Are they gonna like bounce a bunch of stuff exactly vertically? Won't it bounce exactly straight up?
No. It's just on a plastic peg. Okay, so if I drop it exactly vertically, it should bounce up exactly vertically.
Yeah. Oh, it'll go back on the peg. I don't know actually.
Oh, the chances of that are like 0.00. Put a Google number of zeros and then just put a 1 after.
Hey, you never know.
Okay, well, this is science class, and we just do experiments like anytime we want to know. So here we go, and if I don't drop it today, I'm just going to have Andy do it for me next time. Okay, I dropped it pretty close to vertical there. I'm not.
What just happened? I missed it. I missed it.
I didn't even know where it went, Andy.
I don't even.
No, but how did the other 2?
Run that back.
Okay. So we'll do it again. We'll do it again. Max is going to make sure he sees this. Why don't you just come do something? Yeah. That way, Max won't people know I'm not doing anything fun. You play whatever you want.
Ready? I got to drop vertical, right?
Yeah.
Not this one?
Yeah. Hey, you drop that way, you're going to shoot me.
Oh! It fell! That's clean!
Okay, so
clean!
I like that.
So this?
okay.
What happened?
Okay.
Oh, wow.
That's why it has that peg of a wider width so they can't come off. So this one can come off. Thank you, Judith. Why?
You drop it that way. Yeah.
Huh?
You drop it that way.
It's rubbish sideways.
Try it.
Okay, Claudia actually has an answer.
Well, go ahead.
Okay, not so good. Yeah, Link. Claudia, what's your answer?
Well, is it because like the total energy just goes into the last ball?
That's right. What's happening, and people don't ever think about this, when this heat hits the ground, only the bottom part's touching the ground, right?
Yeah.
And so that starts what we call a shock wave that goes up through this, and that shock wave spreads out and then it focuses back and it all comes to this next ball. And when that shock wave gets to this next ball, well, then it sends a shock wave through it, shock wave through that, and you're transferring momentum with that shock wave. And so when it gets to the final ball, all that momentum transfers to this one, gets up to the top, and it goes flying off.
Isn't that how pool works?
How it's cool. Well, pool is much more like what I'm going to do up here. You're not doing as much of just transferring all out of this, and this into this. But now we weren't putting 100% of the energy into this, obviously. But we were probably putting half of the energy of this entire thing into this little ball. But kinetic energy, 1/2 mv squared. Take the energy of all of these and put it in this little ball, and it goes a lot faster to me. And you can do this for fun, like you're in the gym. You can just take a basketball and a volleyball. Put the volleyball on top of the basketball and drop them together. It's a little harder because you don't have everything set for you. And it'll shoot the volleyball up. If you put it the other way around, it won't be as exciting because, of course, the mass of the volleyball is small compared to the basketball. You can just maybe. That was a bad plan. I feel like I caused more too, so that's why I said it's a bad plan. Okay. There's one more somewhere. Thank you. So that was a demonstration that had transfer of energy, but also there was a clear momentum issue there. Now I have these two balls, and let's see. I will go to Aaliyah because she's sitting in a different place than normal. Compare the two balls.
No, it's oh my word, this one has a little scratch on it. So does that one.
Okay, so what's the difference in the two? I didn't hear you. Okay, she said there's no difference. So I'm going to take these two and I'm going to drop them.
Wow.
There was a difference. They're the same color, the same mass, they look the same. What was different about the elasticity, the coefficient of restitution? This one here had a coefficient of restitution of, what do you say, 70% or so? This one here has a coefficient of restitution of, I don't know, 0.1.
If that.
What's the difference? How do they make them have a different coefficient of restitution?
They have the same mass.
Material.
Is it the material?
It's the material. This one here is more like putty. You can actually squeeze it and you let go and you feel it, that your fingers come away from it as soon as you let go instead of when you reach the radius. This one here, you squeeze it and it'll stay on your fingers until you come back to the radius. You can tell there's a difference. This one is slow to respond, this one's fast. Yes.
Can Aaliyah have those back for a second? I want to change that.
Okay, she's going to alter her answer.
Yeah.
Can you tell the difference when you squeeze them? It doesn't quite feel the same. So Nana's going to squeeze one, Sarah's going to squeeze one. They're going to tell you how they feel different from each other. Now, one of these has a high coefficient of restitution, the other doesn't. Important things to think about. Now, I have this little mallet, and 1/2 of the mallet has the one with the low coefficient of restitution. The other side of the mallet, high coefficient of restitution. So, what I'm going to do, okay, that's low. This is the low side. I should actually write on this. LH. Make sure I put the same thing on both sides. Because it would be crazy to have one side correct and the other side not. Okay, so I'm going to put it with the one with low coefficient of restitution. And I'm going to bring this up here and set it so it just touches. Now I'm going to pull this back so that the end of the ball is even with this little weight hanger and let it hit this block. What's going to happen?
Stop.
stuff. It might fall over. This is the one with the low coefficient of restitution, the non-bouncy side. Make a noise. They're just going out in the limb.
It's gonna hit and not bounce. Yeah.
Okay, hit and not bounce very hard. What's going to happen to this if this doesn't bounce very much?
It's gonna fall over.
Okay. Twist it a little.
Yeah.
Can you bring it up higher?
Oh, I can. Yeah, sure.
You gave it torque.
That's more, yeah, it's all. There
Do it.
Okay. Now, keep in mind, I'm doing a comparison, so I'm bringing it back, and I'm going to pull it back to the same level again, just so we have. That's what happens. Now I'm going to flip this around so it's on the side that's bouncy, the side with the high coefficient of restitution. Maybe. You know, I can't really see that well anymore at old age. It's like,
It would probably help if the projector were shining through your face.
I don't know. It probably helps if I was on the other side of it instead of this side. Okay, so now I set it up for the same arrangement, bring it back to the same height. What's going to happen when it hits this time?
It's gonna bounce back.
Okay, the same thing is going to bounce back. What's going to happen with this?
It's probably gonna stay still.
Okay.
Boom.
Well, that was wrong.
That was awesome.
Why did it fall over when I hit it with the bouncy one, but it didn't fall over when I hit it with the one that wasn't very bouncy?
No, they didn't fall bouncy when absorbed it.
No, the other way. I had to pull it way back to make it fall over.
Is it something about the bouncy transfer all the energy over?
Okay, well, it has to do with momentum. One of these collisions we would say is elastic, at least it's 70% elastic, right? Because it returned about 70% of the energy. One of them was inelastic, it just absorbed it. But what's really important to us with analysis of this is not energy, but simply momentum. In the first case, let's take the gross approximation that when I hit with the low side, it just hit it and stopped. In that case, considering the momentum that this had at the moment it hit it as P, how much momentum was transferred to this? All of the P was transferred. So this had momentum P, and that momentum P wasn't enough to tip it. Now when I turned it to the bouncy side, it bounced back with about, let's just make it easy and say that it was perfect. So it bounces back with the same momentum it hit it with. And so the transfer would have to be 2P. This would have to have twice as much momentum because the change in momentum of the hammer the first time was going from P to 0. The second time it's going from P to minus P. So the change in momentum is final minus P minus initial is minus 2P. And so 2P had to be transferred to this, had twice the momentum, it was going twice as fast. That's why it fell over. I find this stuff really fun. I hope you at least find it illuminating, if not fun.
Do you mind writing out what you just said with the P, the negative P, and the 2?
I do not mind at all.
Awesome.
Well, because it'd be P equals 0, and then P1 equals negative P.
Right?
I'm actually going to do it in gross detail.
Awesome.
Yeah, awesome.
Like gross like disgusting or gross like lots?
Gross like lots.
Awesome.
Gross like the German word gross. Es ist sehr gross. Okay, so in both cases, we start with the hammer like this, and we have it at some elevation H above where it will be when it's vertical. And so we're going to have the potential energy. It starts with converted to kinetic energy before the collision. So we start with potential energy initial is equal to mgh, kinetic energy initial equals 0, and then potential energy 1, notice I used 1 here. I'm going to use 0 here for initial so that my 1 looks more distinct, is equal to 0, because I use this as y equals 0 for my reference. So I start with that calculation. So I can calculate how fast it's going just before it strikes. And remember, I had it set up so it was hanging vertically at the point where it's going to contact. So this was the point of contact. So how do I find the speed at position 1? Go ahead, Judith.
Just before we get into it.
Before we get into the problem, yeah, sure.
The dash rectangle, is that the block that we were?
That's going to be the second position at the moment,
Oh.
immediately before it strikes the block.
Okay.
Right, because I have set so it's in the straight up and down for the rod just before the time hits.
Oh, okay.
So we've done a bunch of work energy problems. How do I find the speed at this instant?
We set MGH equal to 1/2 mv squared.
Okay,
GH.
that's the rubber hits the road, but if you use that as your rule, you're going to make a lot of mistakes
You have to use the non.
because that's what works here, but not always.
You have to use like the biomass initial plus the batch people with non-conservative and so on or something.
Okay, yes. The process is first you identify what the kinetic and potential energies are at the beginning and end, and then the work non-conservative. What would cause a non-conservative work? Friction would, but we don't have friction here. What else would?
Air resistance.
Air resistance. We do have air resistance here, but unless it's explicitly said to use it, we assume it doesn't exist. What else? Not really.
Okay.
Heat is a transfer process. That's why I'm not really. Could also have had somebody pushing on it. That would be non-conservative. You know, there's some other options, things we need to think about. But here there were no non-conservatives. None of those things existed. It was just gravity and the support holding it up. And so then you apply the work energy relationship in the form of work non-conservative is equal to change in kinetic energy plus change in potential energy. And so that's going to be 0 equals kinetic energy final, which has the equation 1/2 mv1 squared minus kinetic energy initial, which was 0, plus potential energy final, which is 0, minus potential energy initial, mgh. Now remember I said where the rubber meets the road, it turns out that in this case, the final kinetic energy is equal to the initial potential energy. But that is not generally a true statement. So just saying mgh equals 1/2 mv squared is generally wrong. Especially because if you say it that way, you're not even specifying it's mgh here compared to 1/2 mv squared at a different time and location. Right, so it's important to be careful with that so you don't get in a problem and make a blatant mistake where it actually is as simple as doing this every time. So now, notice the mass is canceled. It doesn't matter what the mass is. And I have V1 squared is equal to 2GH. Or V1 is equal to square root of 2GH. And of course, it's technically plus or minus. It could be swinging forward or backward. We don't care in this case. That's the speed. Why did I calculate the speed? Because the speed is part of momentum. And I said I was going to do it in gross detail. This is the gross part. I could have just said it has some speed V. But we've just gone through this work energy thing, and I want to make sure we have as much practice with it, seeing it applied to something real as we can. So now we come back actually to this picture, and now we're at this location, and it has momentum P1 is equal to mv1 is equal to m square root gh. Is that right? 2gh times 2. I got room for it. So that's our momentum it has just before the collision. And then we have two separate types of collisions, so I'm going to separate them. Up here we have the what we call elastic collision. Bounces back perfectly, which we're going to take to be momentum 2 is equal to minus momentum 1. Now we look at this, momentum does have a direction. For our purposes, I'm just going to consider this the positive direction. Well, I can't do that. It's not in my DNA anymore. It's been drummed out of me. By convention, we take to the right as positive. So I'm going to call that the negative direction. So momentum 1 is minus m square root 2gh. So momentum 2 is minus or plus m square root 2gh. And so the change in momentum for the hammer is equal to momentum 2 minus momentum 1, which is going to be m square root 2gh minus negative m square root 2gh equals 2m square root 2gh. So the change in the momentum of the hammer in the elastic case is it started with the momentum of P1 going to the left in my picture there. I drew the picture from the way it looked from my side of the table, not from your side of the table. I'm sorry about that. I didn't even realize it until I came around and looked at what's up there. Go ahead.
Why do we have m squared gh squared when?
No, that's not squared. That's multiplied by 2.
Okay.
Sorry. It down below I had square root 2
Right.
gh, and I just forgot the 2, so I put it there.
Okay. Can you go back over to the other part?
Ooh, this way?
Yeah.
All right. I'm really good at this, apparently not. So my change in momentum for the hammer was positive 2m square root 2gh for the elastic case. For the inelastic case, inelastic actually means, well, perfectly inelastic means that they stick together. That's perfectly elastic. That's part of today's lecture material is this elastic and inelastic, so I'm going to talk about them some more. But in our case, that's going to be, in practice, momentum 2 equals 0. And so the change in momentum of the hammer is equal to the momentum final minus the momentum initial. It's still that equation. M square root 2gh. So the change in momentum for the hammer was twice as much in the first case as it was in the second case. That's writing out all of the math to go along with the words I said. Except for one thing. We have a collision here, and if the net external force on the participants in the collision is 0, then momentum is conserved between the two participants. Even in the case of the non-bouncy ball, the collision was really short in duration. And so that net force isn't 0. Clearly, one's pushing on the other, but we're looking external, and the external forces are really going to be small because there was, the instant before the collision, there was no side-to-side friction acting on the block. The instant after the collision, there will be, but during the collision, there essentially is not. So momentum is conserved during the collision, which means that in both cases, momentum before is equal to momentum after. And that's immediately before versus immediately after. And so since the hammer changed by a factor of 2m squared 2gh in the first case, then the block had to change by the same amount in the opposite direction. So the block had to have a change of minus 2m squared root 2gh for the first case. In the second one, it was only minus m squared root 2gh, so half as much change in momentum. And then if you look at kinetic energy, if you have half the speed, how much kinetic energy do you have? Proportionally, of course. Kinetic energy being 1/2 mv squared. If you square 1/2, you have 1/4. So it had 1/4 of the kinetic energy after the collision when I had the non-bouncy one compared to when I had the bouncy one. That helps to illustrate, by the way, the difference between energy and momentum, because often kinetic energy and momentum can be confused. In fact, historically, they were confused. It was a while before they realized, no, these are two distinctly different things we need to work with. All right, we're ready to get started with the lecture. What do you say? We're halfway through. Innovations for car safety. Name for me 3 innovations in a car that make it safer than they used to be. Russell. Seatbelts. And airbags.
And crush points.
All right, those are the 3 that I identified, which is why I said name 3. You have crumple zones. He called them crush points. Same thing. What's the point of a crumple zone? Okay, you're absorbing energy into the framework of the car, which means there's less for the occupants, the human occupants, to absorb. That's good. What's the point of the seat belt? Okay, to keep you from flying into something. Now, in the early days of automobile safety, they made lap restraints. So you put a lap belt on, and you're driving at 60 miles an hour, and then the car stops. We learned the first law of motion that says that you are going to continue at constant velocity unless something acts on you. And since you have a hinge point here, you guys have started reading chapter 9, which is starting to talk about momentum, or angular momentum and torques. You have this mass up above it, and you're pinned at your waist, so the front mass has a pivot and goes, woo, and goes flying forward. As an EMT, the first patient I ever had, he'd been tweaking for like 3 days. He fell off a ladder, hurt himself. He didn't have a license, go figure. But he had a car, and he's like, I'm going to drive to my mother's house, and then she can drive me to the emergency room. But he fell asleep on the drive and hit a tree. And there was a nice little star pattern on the windshield where his face hit it. Why? Because you pivot forward if you don't have a shoulder strap on, or in his case, I don't think he had any restraint. But the shoulder strap would just make it a little worse, or excuse me, the waist belt, seat belt would make it just a little worse. You swing forward, your head's actually going to be going faster than it would have been without it, and whammo! It was really bad. His nose was undefinable. He just looked like a person with no nose. And I told him he was on drugs. He was like, does it look bad? What I told him was, you're not going to win the beauty contest. What I put in the patient care report was his nose was undefinable. So we have those lap belts, and it turns out those aren't very good safety things. So what did they add to the lap belt? Shoulder strap. Now the shoulder strap keeps you from swinging forward. But of course, is it perfectly safe? No, why not?
Because, yeah.
You can get a pretty bad bruise from it. Russ has a question.
Also, they don't put the shoulder straps on planes.
Like they don't put shoulder straps on planes? Look, buddy, you're dead. Yeah. I mean,
He said
the point of the seatbelt on an airplane is not in case of a crash. It's if you have turbulence, we don't want your head to hit the roof. There was a case, I don't know, probably 20 years ago now, where an airplane hit turbulence, somebody flew up, their head hit the roof, and they broke their neck and died. Right? If they'd been wearing their seatbelt, it would have been fine. Different situation. If it crashes, yeah, it doesn't matter.
Good luck. Well, it's probably easier to identify
Just
people
keep
with the crashes than we have to see. But
Okay, we can IRR major.
But back to
Yes.
there's different types of crashing.
There are, but what do we worry about? We worry about the ones that, are major. Anyway, getting back to the cars.
a minor airplane.
So they have improved cars, except for the Yugos. I don't know if you guys remember the Yugos.
Yeah.
What?
I have something to say about safety belts.
I still cannot hear you.
I have something to say about safety belts.
Okay, she has something to say about safety belts.
So, I'm not convinced exactly. It's like, if we, take the whole extent of the length of your safety belt, I think that's how you're supposed to learn.
Okay, you should wear your safety belt so it is snug on you. Now, safety belt technology has improved dramatically since I was a kid. I mentioned the Yugo because the Yugo was the last one that I know of that the belts were bolted in place. So you had basically a non-stretchy canvas belt. That's going to cause, like Matt was saying, a lot of pain when you get in an accident. But these days, that's not what they do. These days, well, first of all, you have things like you can pull it out and back, you don't have to adjust it right, it adjusts itself. And it freely moves, if the car is working right, unless you hit the brake. If you hit the brake, then it locks the seatbelt so it won't freely move. So you have free motion unless you get in an accident. Good, right? But furthermore, those seatbelts are not bolted to the frame anymore. They are coupled through a spring to the frame. So when you get in an accident, that seatbelt will stretch with you to some degree because of the spring. What is that going to do? It's going to make it so it takes a longer time for you to stop. Why would a longer time be good?
Less force.
Less force, right, because impulse was the net force multiplied by the time it acts. If you increase the time it acts, you lower the force. And so it's safer because it has those springs. Now we turn to the airbags that you can see in here. You can see both shoulder strap and airbag in this picture. What's the whole point of an airbag?
Cushion.
Cushion, yes, but let's be a little more specific about that cushion factor. What's it doing fundamentally?
Braking.
Slowing down your competitor.
It extends the time for you to stop again. That thing has an explosive in there that makes it deploy. Guess how fast an airbag deploys?
Really fast. Extremely fast.
Well, in miles per hour.
Oh.
It's the only thing I know the answer is. It comes flying out at you at about 200 miles an hour. If you are short, that is a danger. So people that are really short, I believe it's federal law, can go and have their airbags turned off because it's more dangerous to them to get hit by that airbag than it is providing safety features.
How short are we talking?
I think we're talking like less than 5 feet.
That's why you're supposed to wait for 12 years of age or something.
If you're a grown adult and over 5 feet tall, which you happen to be, then it's probably okay.
But like once you're a grown adult, but you're not under 5 feet.
Well, then that's when you go to the dealership.
Okay.
It's I would like these to be turned off. Was
There's
that?
actually a lot of people that are also
Yeah, and those are the ones that are in danger from the airbag.
Why don't they make airbags that are like
Miniature.
Like what about the like cars that are like really small? Like the mini cars.
Like the small car.
Like the only kids.
Honestly, I don't know.
So like why would you have airbags be that much still? Like doesn't it?
Well, yeah, if your car won't fit somebody who puts the seat this far away, then you don't need an airbag that deploys that far. Right, the reason you have problems is if you have tall drivers and short drivers. The tall driver sitting way back, the short driver sitting really close. If you have a small car that only small people can fit into, then it's going to be adjusted for shorter people to begin with. I'm saying all of this without any specific knowledge, just general principles. Okay, so the point is the airbag comes out at 200 miles an hour. It, she was talking seconds, it's a split second for it to be fully inflated. What do you have in the back of your airbags? Big gaping holes. So they instantly deflate. But the holes are this big, and you have that big explosive that made it expand. And so it deflates very quickly, but it's going to slow you down, and the hole is designed to make it so it will deflate and keep a force that is reasonable for the body while it slows you down. Once again, extending the time, lowering the force that you have to have. There's another thing about those airbags that's very useful. They keep glass from flying in. So I didn't put that picture. I had another picture I was considering that showed the interior of a car that has 18 airbags. We've seen those advertisements for cars. And they have the side window airbags that if you have the right kind of collision, they actually have sensors to determine what direction the collision is for which they're going to deploy, because there's money involved in the time you deploy one. but those side curtain airbags come down, and they're going to keep glass from coming in. So there's another aspect besides the momentum issue that I'm talking about here. And then the final one, the crumple zones. The crumple zones also will make the collision last longer, and they're scrubbing that energy. So there's a lot of technology that goes into making cars safer. And, you know, we often ask, why do we have things like automobile racing? It's because we like to watch people drive fast and hit hard, right? But there are also, yes, we like to go. There are also a lot of nice innovations that come from that help us in our everyday lives, things like safety procedures.
I have a question.
Go ahead.
Okay, for people that are like called NASCAR drivers, are their seatbelts and safety things different than are the normal cars?
Oh, yes. Especially after Dale Earnhardt Sr. died the last lap of the Daytona 500. Yeah. So, yeah, they have a 5-point harness, and they have obviously a helmet. And I believe that their helmets, it depends on what level you're, which racing series, but a lot of them, the helmets are actually held in place so that your head can't go like that.
Like a reverse, like you want it going, like wouldn't that be like a, I don't know.
Well,
neck lap?
you don't want your head to go this or this.
Yeah.
And by the way, just one thing we learned from EMT class that's really important, my wife completely ignores and says I'm stupid. Headrests.
Oh, true.
What's the purpose of a headrest?
Keep your head flat.
To keep you from breaking your neck, right? If you're sitting and somebody rear ends you at 60 miles an hour, you don't want your neck to be snapped off. That's why you have a headrest. So it should be there so your head is touching it. My wife's like, oh, that's a nuisance. So she does other things with it. Well, if you take it off, then you just have something that will nicely shear your neck off if you, get rear-ended. So don't do that, okay? Yeah, it keeps you from suffering. In case of debilitating car crash, you have no suffering. Okay. So the whole key to the automobile safety that we were talking about was this relationship that the change in momentum, because you're going to go from whatever your speed was to 0, is dependent on the net force. The net force is changing momentum or changing time. If the change in time gets longer, change in momentum stays the same, and the net force gets smaller. That's the whole purpose of these things we've been talking about. Well, the major purpose. Oh, yeah, here's the other picture I was talking about. I did put it in. So you see the side curtains. Obviously, one side of the car has been removed. What'd you say, David?
That's a lot of airbags.
Yes, it's a lot of airbags. And they're all deployed. What kind? I don't know. I don't know if it's identifiable, but certainly it's not by me. Okay, so let's get to doing some problems. We've talked a lot. This is my last day on momentum. We're going to be talking about momentum in lab tomorrow, and then Wednesday it'll be torques and that kind of thing.
Then you last. This isn't your last day.
It's my last lecture, sir.
Or you're still going to lecture about it tomorrow.
Not really. Okay, so doing a problem. Inelastic collisions. I put these in reverse order because to me, it makes sense to put the easiest one first. Inelastic collisions are easier than elastic. Why? Inelastic means that you have, let me adjust so you can see the bottom of that line just in case you're reading it. Inelastic means, in our case, that they stick together. In reality, elastic means that it will come back to where it was and return kinetic energy. Inelastic means you have permanent deformation. But for our cases, inelastic will mean they stick together, okay? So when I say inelastic, I mean they stick together. If two things stick together, you have one equation that's really simple. The final speed of object 1 is equal to the final speed of object 2 if they stick together, right? So anytime you have an inelastic collision, you say, aha, V1 final is equal to V2 final, where 1 and 2 is identifying the object, and final, of course, is after the collision. Well, that makes life easier. That's a simple equation to work with. As we'll see in a moment when we get to elastic collisions, it's going to be more complicated. So I have an example here. Two objects of equal mass initially head directly toward each other at the same speed, stick together. So let me make sure I have these the right way so they will, yeah. So if they're coming exactly the same speed toward each other, what can you tell me about the momentum of the two cars? They're the same but in opposite directions, right? So what's the total momentum?
Yeah, zero.
So if they have the same final speed and the total momentum is conserved, why would the total momentum be conserved? Because the amount of friction multiplied by the time of the collision is very small. What would their final speed be?
Should be zero.
Should be zero because you have mass 1 plus mass 2. So final momentum is mass 1 times velocity 1 final plus mass 2 times velocity 2 final. But if velocity 1 final, velocity 2 final same, it's just mass 1 plus mass 2 all times final velocity. If it's zero, final velocity has to be zero. So let's see how well I can do this. Okay, so it wasn't at rest. That tells you that the one on the right was going a little faster than the one on the left. What about a case where this one's cruising along and it hits that one at rest? What's going to happen? Okay, it'll go half as fast because your momentum was m times v1. Now it's m plus m, or 2m, times v final. What if I do something like this? I'll put a mass in here. So the heavier one is going to be stationary. The lighter one's going to hit it. What's going to happen? Faster or slower? Slower, because we had 3m in the final case instead of 2m. What if I put it in this one? Then what happens?
Should be faster.
It will not lose as much speed. In fact, you can hardly tell there because my speeds were so slow. You're going to be measuring stuff like that in lab tomorrow. So in these cases, you just have two relations that you use to solve them. Momentum initial equals momentum final. I wrote as a vector equation, but remember I told you we're always going to do the one-dimensional for this class, so the vector equation is not going to be important to you per se. And you have V1 final equals V2 final. And so you just calculate what the momenta were before, the momentum were afterward, putting in variables that you don't know, and solve with those two equations. In theory, how many variables could you not know if you have two equations? Two, right. So if I know, yeah, let's just move on. I gave a problem here. Because I only have 8 minutes left, I'm going to skip over this problem because we've already done essentially the work of it and go to the elastic collision. So the elastic collision is, for our purposes, going to mean that kinetic energy initial is equal to kinetic energy final. Now, this turns out to be much more complicated because you always have momentum is conserved. So you have mass 1, velocity 1 initial, plus mass 2, velocity 2 initial is equal to mass 1, velocity 1 final, plus mass 2, velocity 2 final. You always have that because that's conservation of momentum. Go ahead, Oksana.
Are those just the derivatives?
Those are not derivatives. Those are momentum is equal to mv is conserved. So this is momentum of 1 initial plus momentum of 2 initial equals momentum of 1 final plus momentum of 2 final.
You have P prime over in the illustration.
The illustration is using primes to indicate final, not to indicate a derivative.
Oh, okay.
So we have that relation. Now I'm going to manipulate this equation in a way that initially looks nonsensical. So it's something when we get to the end, it'll make sense. When we start, it looks dumb. I'm going to combine terms by mass. So I'm going to subtract m1v final from both sides. 1 final. And I am going to subtract, that's a bad choice of pen color, subtract m2 v2 initial from both sides. And so now I can factor out the m's. So I'm going to have on the left side m1 times v1 initial minus v1 final equals M2 times V2 final minus V2 initial. Notice one side had initial minus final, one had final minus initial. It's important to notice that distinction or you start thinking we've done some funny things.
Should be a negative M2.
I have positive M2 and then I have a negative with the V2 zero. So that is another way of writing the conservation of momentum equation. So these two are equivalents. They have exactly the same information. But now we go to conservation of kinetic energy. Remember, conservation means doesn't change. So I'm going to have my kinetic energy initial, which is going to be kinetic energy 1 initial plus kinetic energy 2 initial equals kinetic energy 1 final plus kinetic energy 2 final. Now, before I do any work, I'm going to do the same thing. That is, I'm going to subtract kinetic energy 1 final from both sides and subtract kinetic energy 2 initial from both sides. So I have kinetic energy 1 initial minus kinetic energy 1 final equals kinetic energy 2 final minus kinetic energy 2 initial. 0. And once again, I emphasize, I understand that it looks like I'm just doing more work than necessary up to this point. In 2 lines, you'll see the magic of why I'm doing it. What do you think should be the next line?
Carries, take out the carries.
The K stand for kinetic, so I can't take out the K. I can replace KE with 1/2 mv squared, right? Because kinetic energy is just saying whatever it is. The equation is what I really need. So I need to put 1/2 m1 v1 initial squared minus 1/2 m. I will.
And the 1/2.
And the 1/2. Make sure we realize that was a V1 final. So I can first multiply everything by 2 because you would be crazy to keep 1/2 in every term. And then I'm going to factor the m's as you said. So I'm going to have m1 times v1 initial squared minus v1 final squared equals m2 times v2 final squared minus v2 initial squared. And now the magic. The magic is to recognize that V1 initial squared minus V1 final squared is V1 initial minus V1 final times V1 initial plus V1 final. Yes, sir.
Never mind.
Okay, I won't. So that's my left-hand side. My right-hand side is like unto it. V2 final minus V2 initial times V2 final plus V2 initial. But the thing is, this equation right here, that term is this. And this term is this. So those two things in the boxes from our conservation momentum equation are equal. So I can cancel those with each other.
Wait, they are?
That is what we had.
Great.
And so suddenly this becomes a very simple equation, not as simple as for the inelastic case. V1 initial plus V1 final equals V2 initial plus V2 final. So that's the second equation to go along with conservation momentum when you're doing an elastic collision problem. You can see that's a lot more involved, especially the process of getting there. But it was just mathematical manipulation of the variables. So we don't have time to do these problems. Obviously, I was going to do this problem, then have you do this problem. Instead, I will just very quickly point out how we do this collision example. First thing to do in the example, what type of collision is it if the goalie actually catches the puck? So it sticks with the goalie. It's inelastic. In the inelastic case, I have conservation momentum plus what's the other equation?
Initial velocity is final velocity
Plus.
one.
The final velocity of one equals the final velocity of the other because they stuck together. So I have conservation of momentum and they have the same final velocities. So in the first case, the total momentum was mass of the puck times the velocity of the puck. So it'd be 0.165 kilograms times 40.2 meters per second. This is a pretty average NHL slap shot speed. It's not the highest, it's an average. Plus 0 because the speed of this guy initially is 0. So that's my initial momentum. What's my final momentum going to be? The addition of the two masses times the final speed. So I already have used the second condition that V1 final equals V2 initial when I said the addition of two masses times the final speed. And then I just set those equal. And so I'm going to have, in this case, just jumping to the final answer, V final is equal to V initial times mass 1, V1 initial, over mass 1 plus mass 2. And since the mass of the hockey player is more than 1,000 times the mass of the puck, the speed of the goalie plus the puck in the end is going to be less than 1/1000th of the speed of the puck. So the goalie does not rebound very quickly. All right. Have a great day. I'll see you tomorrow right here for lab. Remember, do the lab pre-lab quiz. Somebody had said there was a problem with the questions in the lab pre-lab quiz last week, but I looked through everybody's pre-labs and all the questions were on topic. So I'm not sure about that one.
I've screwed them too. I got my hand going.
I'm walking up.